Good morning, everyone. Let's go ahead and get started. So today we're going to begin with picking up where we left off last time with logistic regression. And today we're going to be expanding to generalized logistic regression to look at multiple outcome variables. So this is known as multinomial logistic regression. This is a generalization of logistic regression to multi-class problems. So last time we talked about binary outcomes. So this was something like Fk of I so beta 0 k plus beta 1 k x 1 I. So in this function, k is our outcome and I is the observation. So in the example that we looked at last time, we had something like, let's see, it was % Democrat, and then whether the Democrats win. So you have a bunch of stuff here, and then you have ones and zeros here. Okay, and each entry is an I. So this would be 1, 2, 3, 4. And note that here, K only has 2 outcomes. So now we might be wondering, well, how can we deal with problems similar to when we were thinking about with the explanatory variables? When you have dummy variables that represent 1 or 0, you can also have categorical variables that represent multiple levels. And we want to think about that analogously in a multinomial logistic regression, actually, which a lot of people call MNL. So we'll do a similar approach here. So multiple outcomes. So this is F K I beta 0 k plus beta 1 k x 1 I. And I can actually represent this more generically by maybe something like a vectorized notation. Now the k can be greater than 2. And you have a different set of beta for each outcome. Okay, so this is an important distinction. What I'm writing here isn't it isn't just adding, more betas to this first equation. Essentially, each outcome is going to have its own set of betas associated with this. And I think this will be a lot clearer once we do the example in R. But one possible sort of thing or data set that you might see this in, since I work in transportation, one common type of model that I've worked with is like a choice model. So this might be something like you have a choice between 3 different cars that have different prices with different fuel efficiencies. It might be even extended like this. And so in your outcome here, instead of having a binomial outcome, now you can have, in this case, 3 different outcomes. So when we look at the equation from last time, in a binary logistic case, you have, if you'll recall, something like this. Oh, I should also mention a quick correction. Last time there was a question about the difference between a logit and a logistic, and I somewhat misspoke here. So when we consider the form of the equation where you have the log odds, so the log of probability over 1 minus the probability is equal to beta x. This is known as the logit, and we transform that into this equation, which is known as the inverse logit, which is also known as the logistic. So when you do the logistic regression, you are regressing on this equation up here, as opposed to this equation down here, because we can't actually do an optimization on this form. I mean, technically you could, but it would be a lot more difficult. So that's why it's called the logistic. It's just the inverse logit. Okay, so a more generalized form of the logistic would look something like this, and we're not going to derive this or anything. So now we have multiple outcomes, and I'm going to look at the probability of an outcome J. So this is the same as before, but we're going to be looking specifically at the betas that are associated with the J outcome. and that's divided by the sum of, oops, sorry about that, the sum of all the possible outcomes here. So this is a more generalized form of the multinomial logistic, and you can you can then take for every probability the associated betas, calibrate them to figure out the most likely betas given your probabilities, and that's how you calibrate for that. And again, in this class, we're not going to be focused on where this equation comes from, but we do want to make sure we understand what it means looking at this, and how to interpret it and how to run it in the code. So the first thing right off the bat in interpreting this particular equation is that you note each particular term for the probability has some has this term associated with it. Okay, and so in the previous slide, right here, that would be this set of attributes associated with car1. So it's commonly that function right here is in a choice model commonly associated with a utility function, this portion right here. So the utility associated with a particular outcome is measured as something like this. What this means is that the probability that I select outcome J is the fraction, a modified fraction of each utility of every object, right? Because this equation can then sort of be looked at like, suppose you have three outcomes. Okay, so this would be the exponentiated utility of the first one, the first outcome, and then in the denominator, it would be the sum of each of the outcomes. So the probability that I get the outcome one is essentially the utility of that first one divided by the sum of all of the utilities. And so as you look at the structure of this equation, you can kind of see the relationship between the numerator and the denominator as this sort of fractional component of the total utility. And we'll revisit this in a little bit to think about some of the implications of how it's structured this way. Okay, I see a question pop up, one sec. Can the sample set be different for each outcome? I'm not sure I know what you mean here. So the data is all going to be coming in it's not as though the probabilities are and the betas are calibrated individually. They're all in a single sort of matrix, and put together, right? So the reason for that is the reason why you can't separate the data to calculate them individually is because you have to have all the betas being calculated simultaneously for each outcome. So I think the answer is no to that question, but if I'm not being clear, just let me know. Okay. So let's go ahead and look at this in R. So I'm going to need a whole bunch of packages here. And hopefully I have all these loaded up. Yep, okay. So we're going to look at a data set. This is also from the ISLR package called car seats. And we'll just take a quick look at what this looks like. Okay. So this is not going to be the most robust example. I haven't been able to find a really good data set to do a simple multinomial logit. So take the modeling with a grain of salt here. This is looking at children's car seats, and it looks at the sales, price, income, how much advertising there is, I guess how many, the rough population, the price, and then age, education, so some demographics, and then this variable here, which is called shelf lock, which is it's a qualitative measurement of the location on the shelf, whether it's good, medium, or bad. So again, the modeling may not necessarily make a whole lot of sense, but what we're going to do is we're going to do a regression of the shelf location against other variables, specifically looking at price and sales. It's probably more the other way around, but you could maybe imagine that maybe I will place the seat location in a better shelf location if the price is more competitive, or if it's or if it's selling really well. Although it's more likely that it probably sells really well because it's in a good location. I don't know, maybe. Okay, so let's, before we do the actual modeling, I'm going to show a three-dimensional plot of what we're going to be regressing on. Oops, let me get rid of this stuff. So I'm making a Gg plot from the car seats data set with price on the x-axis, sales on the y-axis, and then a separate color for each of the shelf location types. Okay, so it looks something like this. You've got bad locations, medium locations, and then good locations in green. And I guess we can kind of see it goes from red, blue, green like this. And there's, so that's seems somewhat correlated to sales. So we're going to see how well this model does in being able to separate these based off of the price and sales. Okay, so I am using the NNet package to do this. And they have a function called Multinomial, and it's pretty straightforward. This, unlike last time where we used GLM, which is a more generalized function, Multinom knows that you're trying to do specifically logistic regression, and so all you have to do is put in the variables in a similar way as the linear model. You don't need to put the link in the function because it knows that you're doing a Logit link here. And then data from car seats. So we'll run this and see what happens. You'll notice here, as I run the model, it gives this output: initial value, iteration, final value, converged. That is actually the maximum likelihood estimation algorithm doing its work. So as I mentioned before, unlike a ordinary least squares, the multinomial logistic is not an analytical solver, it's a numeric solver, which means that it is essentially iterating through derivatives to calculate the log likelihood function and maximize that log likelihood. And so it's going to continue to iterate until it reaches some kind of threshold, and then it'll say that it converged, and then it'll be able to tell us the value of the coefficients that it solved for. So we can take a quick look at that. Great. Okay, and so when I do a summary of this, we're going to see a set of coefficients. And as I was mentioning, you've got betas that are, you've got a set of betas for your good outcome and your medium outcome, and they're different, right? And so as I was mentioning in the write-up note section of the notes, each outcome is going to have a different set of betas associated with it. And so what you'll also notice is that there's going to be one set of coefficients that are missing, right? We had 3 outcomes: bad, good, and medium, but the bad coefficients aren't here. And so why is that? Similar to the linear regressions that we were doing with categorical variables, you have one sort of base level. And that is getting left out. That's the bad shelf location outcome. Remember that all of these outcomes are relative to each other because we're talking about the probability of a specific outcome happening. And you can calculate the probability of good from its coefficients. We can calculate the probability of medium from its coefficients, and then you can calculate the probability of bad from 1 minus the probability of good and minus the probability of medium, right? And so if I know probability good is equal to, oops, let me erase that. Probability of good is equal to exp like this. I can back out the probability, and I also know probability of medium equals ... Then I can back out probability of bad by 1 minus probability of good minus probability of medium. Okay, so hopefully that's clear. Sort of analogously from last time, I had mentioned this, that you have essentially these probability plots that look like this. So this was, in our example last time, the probability that the Democrats win, right? And then you had a single beta associated with Democrats winning in your, so probability of Dem win is a function of that beta. But we actually have, in reality, a second line that looks something like this. So in this example, we're going to see kind of a similar type of thing where you might have the probability of one outcome, the probability of a second outcome, and then maybe a third outcome, like this. And the whole point is that at any given point here, these always sum to 1. Okay, I'm gonna quickly pause here. Are there any questions? Any folks confused? Okay. Let's continue onwards then. As I mentioned from last lecture, when I do logistic regressions, I tend to find, again, that the coefficients here are not super intuitive. Especially as we're getting to more and more outcomes, you always have to think about the odds kind of in relation to the levels in other outcomes, and that can be really difficult to interpret. And so when we're thinking about like a linear model, I can say, oh, as I change price in one way, I know exactly how the outcome is going to change. But that's actually not quite true here. It's going to depend on interrelationship between the outcome, the different type of outcomes, and the level that you're setting at. So like if I do a marginal change at a price of $100 and I go up $1 or down $1, compared to if I were at $150 for the price and I go up $1 and down by $1, the change in the probability of a good or medium is not going to be the same at those different levels. So I think in general, it just gets much harder to interpret because the functional form of this thing is really weird. It's that, you know, exp of your beta divided by the sum of the exp betas. And so again, I sort of really encourage that when you do these types of regressions, to always try and go back to the probability space, where it does then, I think, become a lot easier to digest and understand. So let's take a look at that. I've kind of written up a script and used a package called effects to do this. I'm not going to go through the code that carefully, but I'll sort of describe what this is doing. A lot of it is just data manipulation. But I use a package called effect that takes the model that we made before, MNL Fit. And what it does, essentially what it does is it does a series of predictions across one of the variables. You can actually do, you can actually vary across multiple variables, but I'm just going to do price for now because I think it'll be easiest to understand. And it will look at the probabilities associated with each of those. And so it really is kind of like a predictive function, a more powerful predict function. It comes in its own package called effects up here. But what you can see here is that it's going to look at the probability associated with a particular outcome. So at price 24, the probability that the outcome is that you're at a bad shelf location is, you know, 80%. At $66, it's 53%. Okay, and so I've gotten that from my effect function, and then what I'm doing is essentially transforming the data so that I can plot it. That's all of this code here, and what we'll see is a graph that looks like this, which I think is quite a bit easier to interpret. Do note that this particular model has is actually varying across two variables, right? We have both price and the number of sales. So in this particular case, the sales are being held constant. The default is that it holds the sales, it holds the variables that you're not varying to their average value. So just keep that in mind. But the way that we interpret this this graph, I think, is a lot easier to understand than it is to understand the interpretation of the coefficients. So as I mentioned before, at any single price point, the probability of the outcome has to add up to 1. So this plus this plus this equals 1. This plus this plus this equals 1. And basically what we see is that as the car seat price increases, let's see, the probability that that car seat is in a good shelf location will continue to increase, okay? And as the car seat price decreases, the probability that it's in a bad shelf location will decrease. And then the probability that it's in a medium location, shelf location, sort of increases up to a certain point and then decreases afterwards. So again, this is working in, it's exactly the same answer that you're getting out of the model for your beta coefficients. But by operating in a probability space, I think it's just simply a lot easier to interpret. Okay.
Alan, what's informing like the spread that you're plotting?
Yeah, so this, actually that's the main reason why I use the effects package. This shaded area is related to the standard error in the coefficients. And so essentially it just means that there is a little bit of uncertainty with my estimate, right? Because my estimate is, or my prediction and probability, because that's all based off of how accurate the betas are. And in the default predict function, you can't easily get the confidence intervals for the probabilities for logistic regression, but in the effects package, you can, and that's why I use that instead of predict. And so these are the 95% confidence interval for the probability associated with the outcome at different levels. Okay. So one other thing that I'll quickly show, and we'll actually revisit this particular aspect of logistic regression later on as we compare to other types of models. This is swinging more over to the sort of machine learning side of this, where I essentially I'm going to make, well, okay, I'll just show the plot. So ignore kind of the background for now, and what we're looking at is the first graph that I showed summarizing what we were going to be modeling. So price against sales with color representing the bad, good, and medium outcomes. So these dots here are the actual data. Now that I have the model, I can actually do a prediction for a given for a given input of price and sales, and I've done that across kind of a whole set of price and sales combinations. So the analogy of what you're seeing here is kind of like in a linear regression, if these are my data points and I draw a line through it, that line represents the fit of the data. In the logistic regression, I've sort of colored in the predicted outcome of my model. And so you can see this kind of background shading as essentially the fit of my multinomial logistic regression. And it's saying, I'm going to predict that, so unlike in the linear one where you have this line, in a logistic regression, you only have essentially a set number of outcomes, right? And so I've got my red bad outcome, my blue medium outcome, and my green good outcome. And the MNL is essentially predicting where those outcomes are going to look like for shelf locations. And so the predicted values of my model look essentially like this. And then you can kind of see where you are doing well and where you're doing poorly, right? And we're later on going to revisit this example to see other ways that you can do this sort of prediction against um, uh, a model with multiple variables with a response variable that is discrete. Okay.
Alan, can I ask a follow-up question?
Yes.
You were saying something about how if we built a linear regression model off of the data points which are plotted. I didn't quite catch like what you mean by that.
Oh, I just meant as an analogy,
Mm-hmm.
if you have a linear regression, you have data that looks like this, and then you have like a line, and we call that line the fit, right, of the linear regression through the data.
Mm-hmm.
So analogously, the fit of a um, multinomial logistic regression is essentially this background shading here.
Oh, I see.
So it's kind of weird to think about, but this boundary thing that I'm drawing right here, that is kind of the analogous fit of our model against the data, as opposed to a line going through the data.
Okay.
Yeah.
So can we think of these shaded regions as more like probability regions?
Okay, so yes, except that, so the previous plot that I showed is representing the probability at a specific outcome. This fit doesn't give any information about the probabilities, okay?
Right.
It's going to basically say that it chooses the outcome based on which one has the highest probability, but it doesn't say anything about if I were to look at a specific point, like, oops, if I were to look at a specific point right here, as opposed to or okay, wait, let me think better if I do it like this. If I were to pick a point here and a point here, in both cases, the probability is highest for the bad shelf location. But
Mm-hmm.
it could be that, you know, the probability is equal to like 0.35 here, but over here it could be like 0.9, right? You wouldn't know the difference. They're
Yeah.
both red.
Yeah.
Yeah, so that is one of the things that you're not going to be able to tell from this particular plot. But if you look at the last plot, you would be able to tell. So if I showed this one again, here we can actually see the probability, the
Okay,
actual
makes sense.
probability. Yeah.
Thank you.
Mm-hmm. And this is the exact plot that I'm using to essentially generate the predictions, right? I'm just saying whenever it's highest, you know, here, 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 here. As I go from price to price, it's going to pick an outcome based off of whichever probability is the highest. So the last thing, that I want to talk about with logistic regression, I mean, there are a lot of different details to learn about this, and again, I would say as you get more exposed to this, and this becomes, if this is one of the things that you're going to be using a lot in your real research, again, I would encourage you to take some other classes that dive a little bit more into this, because it's not possible to get into a lot of the nuances related to this sort of modeling, but hopefully you'll at least be able to run the model and understand what it's saying and be able to interpret the results. But one thing that I will sort of touch on that I think is important enough in terms of some of the modeling, not assumptions, but things that go along with the model, is this thing called the independence of irrelevant alternatives. And so what this is saying is that when so the adding another option or changing an alternative option does not affect the relative odds between the two options considered. So what does this mean? So this is a phenomenon of the fact that the logistic equation is structured in the way that it is. So a quick qualitative example is something like, if I were to make the statement vanilla is twice as good as chocolate. If I were doing this, if I were doing a sort of choice modeling in the context of a logistic regression, and I had this particular outcome where the preference for vanilla is twice as good as chocolate. In other words, the probability that you choose vanilla ice cream compared to chocolate ice cream is twice as high. It turns out that as I add more and more alternatives, that this relationship never changes. Okay, so if we think about it in terms of the equation, you might have vanilla divided by vanilla plus chocolate. And even so, where vanilla, well, okay, so even as I add in a whole bunch of other choices, the probability of vanilla, no matter how many other choices are, is going to be equal to 2x probability of chocolate. So let's demonstrate this a little bit more formally. The sort of quintessential example of this, and some of you guys have probably heard about this, is the red bus, blue bus example. So suppose you have a commute from home to work, and the probability that you choose a car is equal to 0.5, and the probability that you choose a bus is equal to 0.5. Actually, and we're going to say that not just any bus, it's going to be a red bus. It's equal to 0.5. So you are indifferent between taking a car and taking a bus. And then what we are going to do is add a new mode. Blue bus is added. And then we're going to say commuters don't care about color. And therefore, probability of red bus is equal to the probability of the blue bus. Therefore, you would want something that looks like this. You would want probability of the car to equal 0.5. You would want probability of the red bus then to be 0.25, and probability of the blue bus to be equal 0.25. Okay. And so hopefully this kind of makes sense, right? I'm essentially taking my car probability, and that stays the same, and then my bus is getting split into two, where you don't really care about whether you take the blue bus or about the red bus. But IIA, the independence of irrelevant alternatives, doesn't let us do this. Remember that relative odds must stay the same, always. And therefore, probability of car must equal the probability of the red bus, because the relative odds have to stay the same between my alternatives. And if the probability of red bus is the same as the probability of blue bus, then all probabilities are equal to 0.33, which is a little bit weird, right? Now you have a smaller probability of going in the car compared to going in the bus, and that is one of the sort of big drawbacks of this type of modeling. So Logit model has a hard time dealing with substitutes. And there's definitely ways to deal with this, as you can actually make the modeling a little bit more complicated. There are things called like nested logit and mixed logit models, which are meant to try and deal with this issue in some ways. But this is something that you'll have to keep in mind if you're doing this sort of modeling. I is a common issue, and it can really have strong implications on your modeling outcomes, depending on sort of the number of choices and substitution between different outcomes in your data set. And so that's again just one of the nuances, one of the more, I think, important nuances of this type of modeling to know about and to consider. Okay, wait, I see a question. In a choice modeling problem, is it possible that individuals have unequal number of alternatives in MNL? Yeah, so that's possible, but you're never, so that would be something like, so the way I would look at this is if for example, hypothetically, in a survey, you had an individual answer like 10 questions that calibrate his outcomes, versus you ask a different individual and you'd ask them like 8 questions that calibrate his outcome, then I guess you could have a different set of observations for each individual, and that would be fine. You could have some kind of weighting by the individual to weight the coefficients. So wait, okay. Actually, I don't think that's the question you're answering, or you're asking. You're asking more that maybe if you were to do, okay, so I think the analogy would be in like a survey, you would ask someone with 4 outcomes versus asking a different person 3 outcomes. Yeah, so that is possible. You wouldn't, I don't think you would do it in this. I don't think you would try to estimate the coefficients in this type of model. I think it would be a different sort of model. And the reason for that, right, is that the coefficients would be calibrated to a different set of output variables for each individual. And so you wouldn't be able to say anything about the substitutability between individuals with different outcomes, because your betas would be nonsensical for any different set of outcomes. You're describing essentially probabilities of outcomes that are not included in the calibration of those betas. So exactly. So in this example where you have someone that has a car and bus choice versus someone that has a car, bus, bike as a choice, unless they were offered that choice and it just looks like their like car and bus choice for the first individual are non-zero and bike is 0, it wouldn't make sense to do it in this sort of modeling framework. Again, you're gonna have a beta for an outcome that doesn't exist for different individuals. It doesn't really make sense to do it like that. Yeah, I think you would need to do modeling in a different way to do that. Okay, let's take a quick halftime break. We'll start again at 11:10. All right, let's continue on. We're going to divert from our discussion about logistic regression, and actually we're going to go back to discussion about selection and regularization. And we're going to actually revisit that to think about a new sort of technique. So with selection, regularization. The basic concept of what we've been doing is essentially to take lots of data and extract sort of the best model that we can from it, right? And so one approach that we looked at was subset selection. And so this was the forwards and backwards stepwise selection, which hopefully you guys are getting intimately familiar with the homework. But the whole point of this is to reduce the number of explanatory variables or coefficients. And then we had a look at some shrinkage methods. And so this is ridge and lasso regression. And the whole point of this was to shrink the size of coefficients. So rather than getting rid of explanatory variables and coefficients, it's essentially reweighting the influence of specific variables in the model, right? And then today what we're going to look at is something known as dimension reduction. And so what we're going to look at is known as principal components analysis, or PCA. It's actually a lot more common for this to be used in unsupervised learning case, but we're going to show an application of PCA in regression. And in this case, we're going to be, what dimension reduction is doing is to transform predictors. Okay. So if we start with our standard linear regression equation, y is equal to beta 1 x1 plus beta 2 x2, and so on and so forth, to beta k xk. The dimension reduction looks something like this. So I will go back and try and describe this a little bit more qualitatively in a second. So it is essentially creating a new vector of z's to regress on that is a linear combination of my x's. In the specific case of PCA, the sum of my I'm totally blanking on what this Greek letter is called, but the sum of these guys.
The phi?
Phi, okay, yeah, all right, thank you. The sum of these guys is equal to 1. So it's a circle in each dimension. So this is linear combinations from X going to Z. Okay, and then what this does is it's going to transform our regression. Oh, I should say, importantly, M, actually I'll write this in color so that it'll be a little bit more obvious what's going on, is less than K. So now our regression equation will look something like this. Instead of beta, I'm just going to put theta to represent a different set of coefficients. Okay, so first of all, why are we doing this? This is, the concept here is, as you have more dimensions, you have more sort of degrees of freedom with which to fit your data. And this can actually get pretty problematic, especially if you have lots and lots of dimensions. So imagine I have a data set that has, let's say, 1,000 observations. So a good number of observations to do modeling on, but say you have 800 variables, explanatory variables. So the number of variables is actually approaching the number of observations that you have. And in certain fields of data analysis, this is actually a pretty common phenomenon. And that can become problematic because you have so many degrees of freedom. And the way that we've looked at trying to deal with this, right, is subset selection, where I kick out a bunch of variables based off of, how good my prediction is, or I do the stepwise thing forwards and backwards, or I can decrease the effect of unimportant variables. In this case, you preserve all of the data, but you reduce the dimension size so that you regress on fewer explanatory variables, or you're regressing on essentially transformed predictors, and so your Z's are predictors that are linear combinations of your original X's. And so the basic concept here is that you're reducing the number of predictors in your model. And oftentimes this is the type of approach that you would take when the number of predictors that you have is pretty close to the number of observations in your model. And actually, by doing this dimensional reduction, it's actually been demonstrated that you can get better predictions than just to run all of them in a linear model. So qualitatively, I'll kind of show what's going on here. Then the reduction to your Z's, each Z is called a component, and in the Pca model, it's a principal component of your predictors. And what that looks like is something like this. So how is it that, okay, let me actually go back to that. So now there's this question of how do I go about figuring out these phi values. So the way that that those values are calculated is like this. So suppose I have data that's x1 and x2, and I want to identify the first component of a set of data. The component, the principal component is the thing that is going to capture the most variance in the data. And so that's going to look something like phi x minus something like this. I'm writing this sort of as a qualitative notation. So variance is something like this, and I want to maximize my variance by choosing some value of theta. So don't worry about that too formally. What it looks like is I'm going to essentially figure out what the mean value of my x1 is. So let's say the mean value is right here. So this represents x1 mean. Now what I'm going to do to find the principal component is I'm going to draw a line through it that stretches across all of the data. So maybe it'll look, if I draw a line like that, I could draw a line like that. I could draw a line like that. Okay. This is kind of a visual representation of what I'm trying to do here. And so the principal component is basically the longest line. It is the line that it's the line that stretches through all of the data and is kind of the longest, right? Because if we think about the length of the line as sort of representing the variance, the biggest variance is the one that's going to have the longest line. And so that turns out to be this line here. And that's going to be the principal components, or that's going to be your first component. And you can do this for all of the different variables. So x1 like that. You can look at the average value for x2. Maybe that's something like here. And this is x2 mean. And then you can look at the relative size of your principal components of each of your variables. And so the first one is going to be the first component is going to be the one with the largest variance, and then you're going to normalize against all your other sort of dimensions. And so you may end up looking something like, well, actually, I'll just draw on the original one. So in my cluster of points, and I also need to delete that. So the red line is going to be my first component. And so I've essentially captured all of the variation along that axis. And so if I were to rotate this, if I were to rotate this red line to be horizontal, then you've essentially captured all of the variation along the horizontal axis. So so you can think of this red line as kind of a new axis. Then the only remaining variation is along this axis, or it's not just that axis, but it's going to be the longest line in the second component. And so this is the second component. And so these are going to represent your measured fees for, or phis for the dimension reduction model. You could have data that's more sort of spread out. In which case you may have a cluster of points like this, and your principal components might look something like this. So on the left, first component is much more important. And on the right, components are closer to equal. Okay, and so as you do this type of regression, or this type of dimension reduction, so you'll note that the z's are independent of each other. And now there's this question essentially of how many components should I be choosing? Since we select m is less than k, we reduce the number of dimensions and prevent overfitting. Okay, so this is getting back to the same concept that we're seeing sort of over and over again with this sort of selection process or regularization process. In my forwards and backwards stepwise selection, how many steps do I take forward or how many steps do I take backwards? That's going to depend on characterizing the models and then figuring out which one does the best out of sample prediction. And then in the shrinkage examples in ridge and lasso, you are essentially saying, okay, how do I choose my tuning parameter, the lambda? And I choose my lambda based off of which one does the best in out of sample prediction. And so it's the same logic here. How many components do I choose? You choose the one that does the best for your out of sample prediction. And so similar with the other ones, I'm going to choose the number of components, principal components, such that my out of sample mean squared error is the best as possible. So let's dive into R and show that example, an example of PCR. which is principal components regression. So since you guys are more familiar with this, we're going to use the hitters data set. Okay, actually, there's actually one thing that I skipped over that I should probably talk about before we dive into this. So going back to, oh no, I always forget when you stop sharing, the notes all disappear. That's all right. So I'll just write this really quickly. So y equals beta 1 x1 plus beta 2 x2 going to beta k xk. And the dimensional transformation goes to something like this. So in comparison to the subset selection and the shrinkage examples, one of the really big benefits of Pca approach, principal components, is that it preserves all of the data. Okay, whereas in your subset selection, right, you are choosing to essentially omit specific explanatory variables, and then in the shrinkage, you are weighting down the effect of specific coefficients. Whereas with a Pca, all of the information is retained. And in that way, you can oftentimes get better predictions using PCR definitely compared to stepwise selection, and oftentimes better than ridge and lasso. Okay, what is the drawback of doing something like this? When I look at a linear regression, I am able to think about the relation of the beta to a specific variable, and the effect of that beta. In the Pca or the principal components regression equation, you can no longer do that, right? It doesn't mean anything. This z here is some linear combination of all of my x's. So I have no idea how to interpret that. And similarly, these thetas, which are kind of equivalent to the betas in the linear regression in a sort of mathematical sense, in a qualitative sense, they are talking about slopes of linear combinations of your original predictors, which don't mean anything. So it's meaningless to interpret any of these coefficients in my Pca. So when I think about inference versus prediction, I'm like solidly in the prediction area. Now I can no longer make any inferences about specific variables. I can take new data and predict on it, and the model is going to be able to do that, but I no longer have the ability to say how one specific variable influences the outcome. So that's kind of the trade-off that you're making here. Okay, so let's go back to our example over here. Okay, so I'm going to use a package called PLS, and that has a function called Pcr, principal uh, um, principal components regression. Okay, and so here we're going to, so I think everyone should be familiar with the hitters data set, given that it's on the homework, but just as a quick summary, these are just statistics about different players in baseball. And we are going to be trying to predict folks, different people's salaries using the principal components regression. So I'm just going to, so again, with these models, it's all about making lots of explanatory variables sort of digestible, right? And so in the principal components, I'm not going to throw anything away. I could just put the whole sort of kitchen sink into the regression. So it's going to be salary against everything else, which is this dot here. I'm going to be grabbing it from hitters, scale equals true. So in this case, it's going to be doing cross-validation, but I'm not actually doing out-of-sample cross-validation. It's just going to be validating against a subset of the actual data. And I'm going to show the difference between that and out-of-sample in just a second. So let's take a look. Okay. So when I do a summary of the Pcr Fit, it doesn't even actually give you anything like the thetas for your different components. It's running through a whole bunch of different components. So if I had one principal component or two principal components or three principal components, in terms of the number of dimension reductions of the original data. And what it's showing is these numbers are the root mean squared error and cross-validated across 10 random segments. And let's show what that looks like qualitatively. Oop, hang on, I need to put that up. So this is a plot of the mean squared error as I add more and more components. This is essentially the same type of graph that I've shown before, where you have model complexity, right? And so the more complex the model is, in this particular case, that would be like having essentially more components in the model, and then this is your model error. And we know that it looks something like this, right? The bias goes like this, and the variance goes like this, and the total error looks something like this. So that's what this chart is showing. except that it's not doing out of sample predictions. So we don't know what the error is looking like for how it predicts against data that it didn't train on. So we can actually go ahead and write a little bit of code that will do a validation based on out of sample prediction. So what I'm doing here is I'm going to create a training set and a testing set. And essentially it's going to take half the data to train on and half the data to test on. And it's done randomly by doing a new column of true and falses, or a vector of true and falses. And I'm going to rerun the model of salary on everything else using the hitters data set, but now I'm going to subset on the training data and do the validation. And so this is essentially exactly the same as before, but now my errors are going to be trained on out of sample data. And we can see what that looks like. Did I run this? Yeah, okay, and so here I think we can see a more sort of realistic pattern where as you add complexity, instead of saying flat, the mean squared error starts to increase. And that trend is having to do with avoiding the overfitting as you increase the complexity of your model. Okay. You can go in and look at the predictions. So actually, by looking at this plot, I can identify the model with the lowest. I'm actually gonna run this again just to see. So actually, in this case, yeah, so one of the things is that it's actually kind of sensitive to the sampling procedure. You can see that at the end of the day, the sort of mean squared errors are pretty close. And so by sort of random variation, what I'm selecting for my training versus testing data set, you may end up with getting slightly different answers as you run this a couple times. And in this case, so in this particular case, I might look at this graph and say, well, the lowest mean squared error in this sample run is having 5 components. So sort of ignore the fact that there's a lot of variation in this particular example, and I would say if you're dealing with that issue, you would probably want to change the way that you're doing your validation. Instead of doing 50-50, maybe you want to do like a 5-fold validation, which you could do in this context. But anyways, if I choose 5 components, and I'm saying that's essentially the model that gives me the lowest out of sample mean squared error here. I can go in and predict my error, which is going to be the same number here, so this 120,000. And I think a good exercise for you guys is to compare how my prediction using principal components regression, PCR, does compared to something like a stepwise regression, or a ledge or not ledge. I'm combining lasso and ridge and lasso regression. And you can compare how essentially the mean squared error against, say, the same sort of testing set across my 3 different methods would do. And I think what you'll find is that of course it depends on context and the actual model, but in general, I think that you'll find, because principal components preserves all of the data, you're going to typically be able to get the lowest mean squared error when you do this sort of approach. And so in cases where inference is less important to you, in other words, you care less about how one specific variable contributes to the outcome, this type of approach may actually do a better job at predicting outcomes compared to your other regressions approaches. Pca and PCR is a very common technique these days. It's used in lots of different applications. So for example, I do know that the credit companies, not credit cards, the ones that can control your credit scores, so like Equifax, TransUnion, Experian, they all use essentially some form of PCA to figure out your credit score. And so that's it's not actually a regression where you're regressing to a specific outcome. It's more of the unsupervised learning, where you're clustering them into this set of credit scores. But yeah, this approach is used by is broadly used, and just an example, the credit scores are generated from this type of approach.
Alan, I have a question.
Yes.
For the step to plot this validation plot and seeing how the mean square error changed
Yep.
in relation to number of components, is that a way for us to visually select the number of principal components, which would minimize the mean square error?
Yeah, exactly. Although you don't have to do it visually. You could actually ask the PCR to give you the components that have the lowest mean squared error. I was just kind of showing that visually, but it's exactly analogous to in the ridge and lasso regressions, where you can plot the mean squared error against the lambda values,
Right.
or I guess they plot the log lambda, but either way, you can ask for the minimum of lambda, right? I think I showed how to do that. So I don't know off the top of my head how to do that in the PCR. I imagine it's something similar, but you'll be able to extract the number of components based off of the minimum mean squared error.
Okay, I see. And then as a follow-up question, then after you found out that the number of components, principal components, which minimize the MSE is 5, you do the predict function to do like an out of sample cross-validation? Is that what the last 2 lines are doing?
Oh, no. Actually, the PCR function will do that for you if you have like a subset of um, to train on. They have they will treat the subset as your training, and then they'll do the cross-validation against the actual, against the stuff that's not contained in the subset. This was just to kind of show how to do that manually. And so if I wanted to extract, I guess, the mean squared error, you could calculate that as a way of comparing against other types of models. Although I guess it would be the same as extracting the mean squared error out of this model.
Okay, I see. Because the PCR function already selects number of principal components to be 5.
Yeah, you can say number of components right here. Yeah.
Okay, perfect. Thank you.
Yeah. Okay, so a couple questions are popping up. Is there any measure to decide whether we can perform PCA on a data set? Well, I think there's two hidden questions here, or sorry, there's this question and kind of an implied question. So you can do PCA on any data set, just like you can do linear regression on any data set. Whether it's worth doing it is kind of a different issue, right? And so so it may be the case that the number of reductions is going to be maybe the same as and you have if you have the same number of x's as a number of z's, then your PCA is actually in a special case where it's the same as the linear regression, right? And so there are cases where, you know, the linear regression really is the best model, and doing a PCA is kind of unnecessary because it gives you the same answer as the linear regression. But I think what you're asking is, when should we use PCA? Again, because you can use PCA anytime. And typically, people will turn to this sort of method when you are having to manipulate lots and lots of variables, and you don't want to sort of get rid of them. And so, you know, I'll go back to the example that I was sort of speaking about qualitatively. Suppose you have 100, or sorry, say you have 1,000 data points and 800 variables. You know, there's cases where maybe it's some sort of survey or something, and a lot of the questions, the 800 questions, just don't really relate to, you know, the particular variable that you're interested in. And in that case, you know, maybe it makes sense to throw out a lot of variables, and qualitatively you can think about why, you know, if I do like subset selection or ridge or lasso regression, you know, it's okay to essentially get rid of the effect of many variables, either by dropping them out or having the coefficients go to 0, because, you know, the like questions are just not related to the variable that you're looking at. And so in my mind, the like context of the question is kind of driving you towards a particular modeling approach. Whereas, you know, an alternative example might be, so one common field which uses this is in like genomics and genetics, where so maybe I have 1,000 observations, and then I have 800 different like genes or something, and I'm not sure how any of the genes are related to a particular outcome of interest. And in that case, I don't want to get rid of anything, and so I throw it all into a PCA. So again, I think when you should use the PCA is highly context specific. Again, to reiterate, I think the typical approach is really to consider this tool when your number of variables are really approaching the number of observations, and you don't really want to get rid of anything. I think that's commonly when you use this. Although, again, because it can be applied in any sort of model that you would do, like a linear regression, it's not a hard and fast rule, right? You don't only need to run PCA when your k's are close to your n's. So hopefully that gives some perspective about when you should use PCA. Okay, I see another question. This is actually more about the coding. So complete cases, what does this do? It's actually pretty simple. Complete cases is a function that will return only values that don't have an NA. So it's going to drop any rows that contain NA in them. Yeah. Okay, so I think we are done for today. Yeah, we're right at the end of our schedule, so same thing as usual. I'll stick around for any questions. Otherwise, I'll see everyone on Thursday. Don't forget that homeworks, I believe, are due end of the day on Thursday, right? So make sure to turn those in. What is my virtual background today? Yes, this is yeah, I actually don't know if everyone's noticing I change my background every day. These are pictures that I've taken over the years. This is a natural gas plant in San Diego that I passed by on my bike tour across the country.